everyone, welcome back. Today we are answering a simple question with a surprisingly big story. How does traffic get from my PC all the way to some devices across the internet? We are going to zoom out the big picture, then walk layer by layer through the OSI model. And we will keep it practical. What addresses matter at each step, what headers get attached, and why it all works. Okay, let's start with a simple analogy. Imagine you're mailing a package. You put your gift in a box, you write the destination and the sender, and sometimes you put that box inside a bigger box, and that inside another bigger box, until it is ready to ship. That's exactly how networking works. We call this encapsulation. Each layer adds its own little box or header, and when the packet arrives, the destination host opens each box one at a time in the reverse order. That is called de-encapsulation. So why do we even use models like OSI? Because networking is insanely complicated. Insanely. If you try to look at it all at once, everything is going to be super complex. Layers give us a structure. Each layer has its own job, and it only talks to the layer above and below it. That way, we can change to fix one part without breaking the whole thing. And for us, as engineers, it makes troubleshooting way easier. Alright, let's go through the OSI model from bottom to top, and I will keep it real world. Layer 1. That's the physical layer. This is literally the ones and zeros moving as electrical signals, or light pulses, or radio waves. If you've got a bad cable, a dirty fiber connector, or Wi-Fi interference, that's all layer 1 stuff. What about layer 2? It is called data link layer. Here, the focus is on local delivery. We package data into frames, and we label them with MAC addresses, the hardware address burned into the network card. Switches operate here. They don't care about IP addresses, just MAC to port mapping. Layer 3 is a network layer. Now, we're thinking globally. This is where IP addressing lives. This layer makes sure your packet can travel from your home network to, say, a server on the other side of the planet. Routers live at this layer. Layer 4 is a transport layer. This is where things like TCP and UDP come into play. TCP is reliable. It makes sure everything arrives in order, and if something is missing, it retransmits that. UDP is lightweight and faster, but it doesn't do all the checks. Think of TCP as mailing something with tracking and insurance, while UDP is like sending a postcard, quick and simple, but no guarantees. And finally, we have layer 5, 6, and 7. Session, presentation, and application in that order. In practice, we usually group these together as the application layer. This is where the actual user-facing protocols live. Your web browser making an HTTP or HTTPS request, your computer using DNS to look up a name, your email client sending an SMTP message. This is the part we, as users, actually care about. Now, I know 7 layers can feel like a lot to memorize, so here is a little trick. Just remember this phrase: all people seem to need data processing. All people seem to need data processing. A is for application, which is layer 7. P is for presentation, which is layer 6. S for session, which is layer 5. T for transport, which is layer 4. N for network, which is layer 3. D for data link, which is layer 2, and finally P for physical, which is layer 1. If you can remember this sentence, you will always be able to recall the OSI layers in order. So what happens when you send data? Let's say you're opening a web page. At the top, the application layer builds the request. The transport layer adds a TCP header so it knows how to handle the conversation. Then the network layer adds an IP header so it knows where to send it globally. Then data link layer slaps on MAC address so it can move locally. And finally, the physical layer turns all that into signals and shoots it over copper, fiber, or wireless. On the other side, the process runs backwards, and signals get turned into frames, then into packets, then into segments, and finally, the application data your browser requested. Different devices care about different layers. Switches only look at layer 2 MAC addresses. Routers look at layer 3 IP addresses. Firewalls might look up to layer 4 or even layer 7 if they are inspecting applications. Hosts like your PC process all the way up to layer 7. And just to anchor this, when we say application layer protocols, we're talking about things we already know. HTTP, HTTPS for web browsing, DNS to translate names into IPs. DHCP so your computer can automatically grab an IP address. SSH so you can securely log in the devices. FTP and TFTP for file transfer. SNMP for network monitoring. NTP to keep clocks in sync. And yes, even Telnet. Though that's basically a museum piece now. So that's the OSI model in a nutshell, and how it applies to host-to-host communication. But I'm just going to map this to TCP/IP model right now. We are going to talk about how we can use this model in day-to-day networking. Okay, so I'm just going to compare this with OSI model as well. TCP is just another way of organizing the letters. It is simpler, only 4 layers instead of 7. At the bottom, we've got the link layer, which covers OSI's layer 1 and 2. This is Ethernet, Wi-Fi, MAC addresses, framing the local hub stuff. Above that is the Internet layer, which matches OSI's layer 3. This is where IP addressing and routing lives. IPv4, IPv6, ICMP, that's all Internet layer. Then comes the transport layer. Same as OSI's layer 4, TCP and UDP ports, reliability everywhere, about making sure apps can share the network without stepping on each other. And at the top, the application layer, which handles OSI's 5, 6, and 7. This is where the familiar protocols are: HTTP, HTTPS, DNS, SMTP, SSH, FTP, and so on. As traffic moves down the stack, it gets different names. At the transport layer, it is called segment. At the internet layer, it is called packet. At link layer, it is a frame. And at the physical layer, it is just raw bits, ones and zeros, on the wire. Same message, just wrapped in different jackets, right? Okay, let's walk it through. I sit at my laptop and type in a URL. Step 1. My browser needs to know the IP of the website, so it does a DNS query. The app creates the DNS request. The transport layer wraps it in UDP with port 53. The internet layer slaps on the IP address. The link layer adds the MAC address, and boom, is out as bits. That frame hits the switch, which forwards it based on MAC. The router strips the frame, checks the IP packet, and forwards it towards the DNS server. The server replies, and now my machine knows the IP of the website. Step 2. The browser starts an HTTP session. That means setting up a TCP connection on port 443. SYN, SYNAC, and ACK, the famous three-way handshake messages, are retrieved. Once that's done, encrypted traffic flows back and forth between my laptop and the server. At every hop, the layer 2 frame is rebuilt with new MAC address, but the layer 3 IP addresses stay the same, end to end. And the port at layer 4 makes sure the traffic goes to the right application on both sides. Okay, if I am on Wi-Fi instead of wire, the principle is identical. The only difference is that the first hop uses 802.11 wireless framing instead of Ethernet. The access point translates it, and after that it looks the same as a wire traffic. Now, I skimmed over TCP versus UDP, but that's important enough to deserve its own video. We will dive into things like transmission, retransmission, flow control, and three-way handshakes, and why UDP is used for voice and video where time is everything. So keep an eye out for that one. And just to tie this back to real applications. Web traffic is HTTP or HTTPS. Name lookups are DNS. IP addresses get handled by DHCP or boot protocol. Devices sync their time with NTP. Admins manage devices with SSH or Telnet. If you're feeling like it's 1995, of course, for Telnet. Files move with FTP or TFTP. Monitoring runs over SNMP. These all right on top of TCP or UDP, and you will see them everywhere in real worlds. And since knowing is only half the battle, I will also be doing a separate quick tool belt tip video. In that one, of course, I will show you the actual commands, like ping, traceroute, NSLOOKUP, Wireshark captures, even using Telnet or SSH, so you can test and troubleshoot what is happening at each layer. So there you have it, OSI, TCP/IP, and PDUs, and a clean end-to-end story of how host-to-host communication works. If you found this useful, please hit that like and also subscribe to the channel. Your support really motivates us to create more content for you. Thanks for watching, and I will see you in the next video.